Let's continue exploring the behavior of graphs and also the average rate of change that we can calculate on graphs. Just like as a reminder, just like in previous videos, if you have a particular section that you want to jump to, be sure to go ahead and look in the description for those timestamps to jump to a specific section. First, let's talk about average rate of change. So the average rate of change, by definition, is the typical change in output divided by change in input over a specific area. So you're talking about 2 points labeled as x1 and f of x1. Another way to think of that would be x1 and y1, since y is oftentimes a different way of talking about f of x, and x2 and f of x2, which again can also be labeled as x2, y2, and you're looking at the change in the function evaluated at x2 minus the change in the function evaluated at x1 divided by the difference between x2 and x1. Slope is a special case of average rate of change whenever you're talking about a linear function, and average rate of change generalizes it to talk about the typical change between 2 points on any function. Let's look at an example. So here we have y representing a year and c of y representing the cost of the gasoline as a function of year. And we have a table of prices below. And as you notice, there's not necessarily a clean mathematical formula to talk about how these prices are related to the year, because we're talking about messy real-world data. And even though it's called y, note that y is our input and c of y is our output. So if we're looking for the average rate of change of gasoline from 2005 to 2012, that's again looking at the change in output. In this case, the output is the cost divided by the change in input. In this case, the input is the year. So we're looking at the cost in 2012 minus the cost in 2005 divided by 2012 minus 2005. Had you listed the cost of 2005 first, you would have to list 2005 first down here. By tradition, we tend to list the bigger x value as x2 and the smaller x value as x1, but there's no law that says that you have to keep it that way. You can change it up a little bit if you prefer. So the cost in 2012 was $3.68, and the cost in 2005 was $2.31, divided by the difference between 2012 and 2005. Between $3.68 and $2.31, that is a $1.37 increase in gas prices, divided by 7 years, gets us a typical rate of change of 19.6 if we're going to round. So approximately, if we're rounding to the nearest cents, 20 cents per year is the average rate of change of that gasoline. And this is, again, just explicitly showing that work if you want to see that step by step. And that's, again, just more reference pages for you if you find it helpful to see written out. But let's go ahead and look at another example. So let's say we have the same data, but now I just want to know the average rate of change just from 2007 to 2009. So even though we found between 2005 and 2012 that the typical rate of change was increasing by 20 cents per year, that might not be the actual change just between those 2 years in particular. Go ahead and pause this video and try that yourself, and then we'll go over it together. So we first want to set this up that this is looking at the cost in 2009 minus the cost in 2007 divided by the difference between the years 2009 and 2007. The cost in 2009 was $2.41. The cost in 2007 was $2.84 divided by 2009 minus 2007. Now here, notice that we actually went down in price, so that should be represented by a negative if we do everything correctly. So $2.41 minus $2.84 gets us negative 43 cents divided by 2 years. So that means that we on average decreased by about 22 cents per year. And this is, again, an average. It's not saying literally every year that's exactly what happened. From 2007 to 2008, for example, we actually went up, but overall that was the average change between those 2 years. Instead of giving you a table, you also could be looking at a graph instead. So we want to find the average rate of change in the interval from -1 to 2. So we want to look at -1, it appears the point is -1, 4. And at 2, it appears the point is 2, 1. So we're looking at f of 2 minus f of -1 divided by 2 minus -1. And again, the key is that you want to keep it consistent. So if you use f of 2 first, you have to use 2 first down here. And that's looking at the change in output divided by the change in input. And again, if this feels like a slope, that's because it really is a more general form of the concept of slope. So f of 2, according to our graph, was 1. That was the y value when x equals 2. F of -1 was 4. That's the y value when x is -1. And then we have 2 minus a -1. 1 minus 4 is -3. 2 minus -1 is +3. -3 divided by -3 is -1. So the average rate of change on that interval was -1. And if I actually draw a pretty good straight line between those two, which that was not the best line in the world, it does actually look like it is approximately a slope of -1. If you're not as familiar with slope right now, no worries, we're about to go over that next unit. I just want to put that seed in your brain a little bit. We also can find an average rate of change entirely algebraically from an equation. So if this is f of x, for example, the average rate of change on 2 to 4 is looking at f of 4 minus f of 2 over 4 minus 2. Again, you could flip-flop the order as long as you stay consistent, but traditionally we tend to list the x2 as the larger x. Now if we're going to be looking here, we want to actually evaluate what f of 4 and f of 2 is, and for me that takes a little bit of work, so I'm going to do that off to the side. F of 4, if I'm plugging into the function, will be 4 squared minus 1 over 4. So that's 16 minus 1/4. And f of 2, that would be 2 squared minus 1/2, which is equal to 4 minus 1/2. From here, there's a couple of different ways you could approach those fractions. I'm personally going to go ahead and convert everybody to fourths just so that I'm dealing with common denominators. So 16 minus 1/4, well, if I think of that as 16 over 1, that means I want to multiply both the top and the bottom by 4. 16 times 4 is going to get me 64. Minus 1 all over 4, so that would give me 63/4. And then similarly here, if I want to convert everybody to fourths, actually let me backtrack and show a few more steps with that fraction, those fractions. If you feel very comfortable with fractions, go ahead and feel free to skip forward a minute or so in the video. So 16 times 4 gets me 64, 1 times 4 gets me 4, so then I have 64/4 minus 1/4, leaves me with 63/4. Here 4 over 1, if I want to convert that to fourths, then I need to multiply both the top and the bottom by 4. That gets me 4 over 4 minus, if I want to convert 1/2 to fourths, I multiply both the top and the bottom by the 2. That would be 2/4. 4/4 minus 2/4 gives me 2/4. And the reason why I did that is because if I was going to do this by hand, that would require a little bit of fraction manipulation, and if I'm going to be adding and subtracting fractions, at some point I need a common denominator. So we have 63/4 minus 2/4 all over 2. 63/4 minus 2/4 gets me 61/4, all divided by 2. Doing this mixed fraction like this, where we have 61 over 4 divided by 2, is the same thing as 61 over 4 times 1/2. So our final answer is 61 over 8 is our average rate of change. If you were on a calculator portion of an exam, it would also be fine to put that into your calculator and use decimals instead. Similar idea here. So I want you, for this next one, the arithmetic actually works out slightly nicer. So I'm going to challenge you to go ahead and pause the video and try to find the average rate of change on the interval from 1 to 9 of this function. First things we want to do is set up what the average rate of change is in general, and that would be f of 9 minus f of 1 over 9 minus 1. F of 9 I'm going to find off to the side. That would be 9 minus 2 times the square root of 9. In terms of order of operations, I first want to simplify underneath the square root first. So that would be square root of 9 is 3. Then you want to do 2 times 3 is 6. So f of 9 is 3. Then you want to similarly evaluate f of 1. That would be 1 minus 2 times the square root of 1. 1 minus 2 times square root of 1 is 1. 2 times 1 is just 2. 1 minus 2 is negative 1. All over 9 minus 1 is 8. 3 minus negative 1 gets us 4. All over 8 for a final answer of 1/2. So still a fraction, but the in-between steps were slightly less messy because we didn't have to convert to like denominators at any point. A lot of times we're interested in looking at whether or not a graph is increasing, decreasing, or constant. And if it's increasing, that means we have a positive average rate of change along that entire interval. That means from left to right, I'm going uphill. Or if you were to sort of think of there being many slopes along the whole line, those slopes would be positive. And that's exactly what it means by this notation, that as long as our x values are bigger, their corresponding y values are also getting bigger. If we're looking at where we're decreasing, that's when from left to right we're going downhill. So that's what it means by the notation down here, that if we're talking about x values that are bigger, now their y values are smaller. And then for this last part, it is again increasing once more. So we always read increasing and decreasing, left to right, same order as we read. If we're going relatively speaking uphill, that means we're increasing. If left to right on top of the function we're going downhill, that means we're decreasing. So let's go ahead and practice some of that. So we want to identify where is it increasing, where is it decreasing, and its domain and range. I actually want to challenge you here to go ahead and pause this video and try to figure that out for yourself. So it looks like here, during this first little interval, when we're talking about x values that are 1 and smaller, that appears to be decreasing from left to right. So I'm going to note where it says over which intervals is it decreasing. First of all, whenever they say over which intervals, it's implicitly asking for which input values. So we're really just paying attention to the x's. So it's decreasing from negative infinity to 1. All of these values over here are decreasing. Then when we read again and we keep going, on this next interval in between 1 and 3, now we're going uphill again. That's going to be a part where it's increasing. Then we start going down again. Between 3 and 4, while it's very subtle, it is still going downhill over that interval. So it's decreasing again from 3 to 4. And then as its last part, from 4 all the way to all x values bigger, it is increasing once again. So if you notice, when I was looking at whether or not it was increasing or decreasing, I only reported which x values that was true at. And in general, that's what they're asking for. They're asking for which x values is it increasing. It's increasing between the x values of 1 and 3, and for all x values bigger than 4. Where is it decreasing? For all x values smaller than 1, and all x values from 3 to 4. And that's again what's going on from left to right. Downhill is decreasing, uphill increasing, downhill, uphill. When we're asking about domain, don't forget that we still know about that. Since we've got arrows on both sides of this, that means we go infinitely in both directions, left to right. So our domain is negative infinity to infinity. For range, however, it looks like we have a very distinct lower bound down here. And that lower bound is at -1, and it does actually hit the point there at the point +1, -1. So we go in terms of y values up and down from -1 all the way up to positive infinity. And that's again just what this is saying in more formal math notation. Increasing means as x gets bigger, y also gets bigger. For decreasing, as x gets bigger, y gets smaller, which I will note as well. Minimum and maximum are pretty much what they sound like. So a local maximum means somebody relative to his neighbors is a peak. He's locally maximum. If he looks to his left and looks to his right, he is the highest point. What is distinct about this idea of local is it means that we need neighboring points on both sides. This is where the most common place where people get messed up. So if, for example, you have some sort of function that has endpoints, you only pay attention to these peaks where there's neighbors. You do not pay attention to the endpoints at all. When we're talking about absolute minimum and maximum, we will pay attention to those endpoints, but not for local. So local, we need neighbors. That's really the key thing. And then similarly, a local minimum means relative to his neighbors, he's a lowest point. So you're looking for peaks for local maxima, valleys for local minima. And that also means that specifically, if we're a local maximum, that means we go from increasing to decreasing. So it always happens at one of those change points. So go ahead and pause your video. When they're asking for the local minimum and local maximum, they're asking for the specific points those happen at. So go and pause the video and see if you can find those. So it appears that we have a local minimum down here at the point -1, -2. And this is actually talking about a coordinate. It's no longer talking about interval notation of particular x values are that way. That's an actual point that occurs at. And similarly, the local maximum happens at +1, +2, and that's again an actual point. And again, we need neighbors on both sides of the point. That's in contrast to an absolute maximum or minimum. So an absolute maximum or minimum, it's absolute, which means is overall the entirety of the graph. If it's an absolute maximum, it's the absolute highest point on the entire graph. So not all graphs have absolute minima or maximum. Now endpoints do count. We don't need neighbors on both sides. And here we have an absolute maximum here at this endpoint, the point 2, 2. We have an absolute minimum at this middle point of 0, -2. And this other endpoint here is nothing special because he doesn't count as a local maximum because he doesn't have any neighbors to the left. And he's not an absolute maximum because this other maximum is bigger. And that's again, all this is saying in more formal language is that if it's an absolute maximum, there is no other point that has a larger y value. If it's an absolute minimum, there's no other point that has a smaller has a smaller y value as well. So this is the highest y value on the whole graph, and this is the lowest y value, so lowest output on the whole graph. And again, it is possible that they doesn't have one. So to determine an absolute minimum, you want to look at all the local minimum and all the endpoints and determine if any of those are the absolute. Similar with absolute maximum, look at all the local maximum and all the endpoints and then figure out who is the highest y value. It is possible that you have a tie as well. All right, go ahead and try these next ones on your own now that we've learned all about finding these extrema. So when we're talking about local minimum, remember that it needs to have neighbors. So here the only local minima will be at the point 0, 0, because these other minimum don't have neighbors. For local maximum, those happen at 2 points. We've got one here at -2, 16, and another one here at +2, 16. We also have two distinct endpoints here. We have one at what appears to be approximately -2.5, 12, and another one down here that appears to be approximately at +3, messing up the writing here, +3, -10. The reason why we know it's at -10 is because it appears to be about halfway through -8 and -12. If we're looking for the absolute minima, we're looking at the lowest of all minimum. So here the lowest y value of all the minima appears here at 3, -10. So that's going to be at 3, -10. When it comes to absolute maxima, we actually have a tie. So we have a tie both between -2, 16 and 2, 16. You also want to pay attention to the directions of whatever problem you're looking at. Sometimes when they're asking for the absolute minima and maxima, they just want the y value and they don't care about the x value. Sometimes they want the full coordinates. So just make sure you're paying attention to those directions. I encourage you to talk to your professor if you have even more questions, as well as look at your textbook. And happy mathing!